Okay, so the goal for today is to talk about policy gradient methods. And because I'm referring to many papers now that are going to be maximizing reward, so we are talking about the era of 1992 to 2002 and then 2015 until now. Okay, so the vanilla policy gradient method was I want to maximize. Let's do maximization. I want to maximize over mu from S to, sorry, again S. Yeah, S is fine, right? Yeah, S to the probability distributions over U. I have expected value of summation t equals 0 to infinity alpha raised to t reward of it ut.
Question here.
Yes.
So previously we always conditioned on the initial state.
Yes, we will. Yeah, that's right. We will be considering two different cases. I0 equals to I, and instead of, let me call this J of mu of I, and then I want to maximize. Okay. Very good point. So let me add another thing. So rho of I equals to the distribution, the probability that I0 equals to I. Let me denote it by vector v mu of I. And now my goal is to maximize rho transpose v mu over all mu. This is the problem that I'm trying to solve. I think now it is set up according to how people have tried to solve it in the past. So rho is the distribution over the initial state. This is the expected reward that you are getting under the policy mu. So ut is distributed according to mu given it, and mu is a policy that's a randomized policy. It's a randomized Markov policy. So mu maps state to probability distribution over all actions. And I'm maximizing rho transpose v mu over this entire space mu. Okay, any questions so far? So in the context of large language models, typically this is the distribution of all queries that people can potentially ask large language models. So that's the distribution over the initial state, that's rho of I. And then this is the total discounted reward that you accrue if you're using the policy mu. And now I want to, now this is a scalar quantity because rho transpose, so v mu is a vector in Rs, rho is a vector in Rs, so rho transpose v mu is essentially the expected value over all possible initial state. And then you're maximizing mu, which maximizes this criteria. Okay, everyone clear? The other thing we talked about in the previous lecture was v mu equals to summation alpha raised to t p mu raised to t r mu t equals 0 to infinity. Remember, this is a vector, this is a vector, this is a matrix, this is a scalar, and I'm taking infinite sum. Okay, so all of you familiar with this? Hopefully, we did a small derivation in the previous class, but hopefully by now you're all convinced that V mu can be written in this particular format. Okay, now I'm going to depart from the original literature in terms of the proof technique. So original literature, the proof was based on expanding this term and then taking the derivative of individual terms with respect to individual mu's. I don't want to do that. And the reason I don't want to do that is because this particular approach, like if you write it in this particular fashion, it's order of magnitude easier to use what is known as perturbation theory of linear operators, abstract theory that's studied in functional analysis literature. So you can use all that technique in order to compute the derivative with respect to mu here. And the reason why that derivative is important is because currently, as we speak, I'm developing the reinforcement learning methods for solving these problems over general state and action spaces. And so that theory is extremely useful for extending this whole stuff that people have done over the past 30 or so years. I can extend it to general state space setting. Okay, so that's why I'm departing from the original proof that you can read in the papers and books.
Is the idea that you can take the infinite sum and write it as like I minus?
Yes, exactly. That's yeah, exactly. Okay. Any questions so far? So now the question from me to you is, now that you know that V mu can be written in this particular format, is there something cool that you notice about this expression? So each of this term, alpha raised to t, p mu raised to t, r mu, is essentially expected value of alpha raised to t, r of it mu ut, right? So this expectation, remember this is an infinite sum and then there is an expectation and they commute, these two operators commute. So I can take, why do they commute? So it is, but remember this is an infinite sum. Okay, so you can talk about the linearity of expectation. If it was a finite sum, then it kind of makes sense. But with infinite sum, you have to be a bit more careful. And the reason why they commute is that the theorem is Fubini's theorem. Don't know how many of you have studied that theorem, but Fubini's theorem, because of Fubini's theorem, you can actually commute this operator. So you can take the summation out of the expectation. And the expected value of alpha raised to t, r of it ut, is essentially given by this expression. Okay. Anything important that you notice here? So I have a vector r mu, which is getting multiplied by something that, some matrix that is raised to t, and I'm taking the sum t goes to 0 to infinity. In particular, this particular vector is common to all of these matrices that it's getting multiplied to. So I can take this vector outside and I can write, let me write it here, v mu equals to summation alpha raised to t, p mu raised to t, r mu. T goes from 0 to infinity. Another thing that you notice is the rows of p mu sum to 1. So the spectral radius of p mu is equal to 1. It's equal to 1. Okay, so I'm multiplying it by a discount factor alpha. So alpha times p mu. So the row of row is already used. Let me write it in the full form. Spectral radius alpha times p mu is equal to alpha, which is strictly less than 1. Okay, wonderful. So I have a matrix with spectral radius less than 1, and I'm doing summation t equals 0 to infinity of this matrix. Anyone remembers the identity? What is this equal to? No?
1 over 1 minus.
Yeah, that is true. If this was a scalar, this is 1 over 1 minus alpha p mu. If this was a scalar, but this is a matrix. It's a square matrix. What's the equivalent in a matrix world? What is 1 minus a equivalent in the matrix world? I minus alpha p mu inverse. Okay, this is known as a Newman series. It's known as geometric series in scalar world, and it's known as Newman series in the operator world. But yeah, that's wonderful. Okay, so all of you agree with this? Now, what do we want to do? What's the origin of what is the origin of the gradient method? So I want to minimize f of x in Rn, and the way I find it is I want to minimize d f of xk plus t for d small. So norm of d is less than equal to 1, or you can put some number here. And then you cannot really do this minimization, so you approximate it as fx plus gradient fx transpose d, and then you find a d which is minimizing, and typically d is minus d times gradient of f of x. This is a positive definite matrix and typically taken to be identity because you want to use steepest descent. You don't want to come up with some complicated matrix, but we'll get to it in a bit. But this is the gradient that we want to compute. So I need to compute the gradient of this whole thing with respect to mu. And in particular, what I'll do is I'll try to understand what is v mu prime minus v mu. What does this look like? So this is same as saying, equivalent to saying, I want to understand what is f of x plus d minus f of x for d small. So I want to assume that mu gets perturbed to mu prime. So I'm sort of making a small perturbation to mu. So I'm making a small perturbation to x. And I want to understand what this term looks like. What does this term look like? This looks like this, gradient of fx transpose t. So I want to understand this particular quantity. Okay. So I need to introduce some notations in order to understand this quantity. Let me write it explicitly. So v mu prime, this implies that v mu prime minus v mu equals to I minus p mu prime inverse r mu prime minus I minus p mu, sorry, alpha inverse r mu. Okay, so this is what we want to understand. And what else do we know? We know that mu prime and mu are close to each other. Okay, so a few entries in mu and mu prime differ by each other by epsilon amount. How would you solve this problem? So I have a matrix inverse. I perturb that matrix, I take the inverse. and then I'm multiplying it by vectors. These two vectors are also close to each other. So what's the approach to understand the difference? So we have to fall back to what is known as perturbation theory for matrices, because I'm perturbing this matrix here and then I'm taking the inverse. So what's the perturbation to a matrix inverse? What does that look like? Okay, so that's what we want to understand in today's class. And then 2 weeks later, when we talk about general state Markov decision processes, I'm going to talk about what the perturbation of linear operators look like. Okay, so we'll spend some time there, but right now let's just focus on the matrix part and try and understand what the perturbation theory looks like. Okay, so I need a few notations. Okay. One general comment, when you are writing papers, you can either be terse on notation and do a lot of math, or you can introduce some notations and make the math easier. Okay, so I'm of the school of thought where I don't want to write long equations. I want to introduce notations so that my equations look cleaner and smaller. Okay, so that's why I'm introducing notations here. Okay, so discounted visitation frequency, and as is the case, I'm running out of notation. So it's d mu of I, which is given as summation alpha raised to t p mu raised to t rho transpose. And then I'm evaluating it at I. So I start from the initial state I0. I look at the evolution of this MDP under the influence of mu. And then I look at what the terminal I looks like. And then, of course, there is an infinite sum. T goes from 0 to infinity. There is an infinite sum. So it's a somewhat complicated. So this is a matrix. This is a vector. I'm multiplying the vector by a matrix and looking at the ith component of that particular matrix. This is known as discounted visitation frequency. Some people would multiply this by 1 minus alpha term, but I'm not going to multiply it. I'll just keep the notation simple. But you can do that. Some papers will multiply it by 1 minus alpha. Second one is sigma mu, which is summation alpha raised to t, p mu raised to t. T goes from 0 to infinity. This doesn't have any name, okay? But this is also equal to I minus alpha p mu inverse. Q function. Q mu is R IU is equal to R IU plus alpha summation Pij u v mu j. This is summation over all j. So Q function is reward function plus alpha times the expected future value, but the future value is evaluated at mu. That's my Q mu function. This is known as a Q function. Advantage function. This is A mu of IU equals to Q mu of IU minus V mu of I. and another function called policy advantage function. L mu prime summation t equals 0 to infinity and I can write this as sigma mu times r delta plus alpha p delta sigma mu r mu, and delta mu prime minus mu. No. Perfect. Okay, so let's look at the notation. The first one is discounted visitation frequency. It's a row vector. This one is a matrix. We all understand what this matrix is. It's an infinite sum written in this fashion. Q function is something we are all familiar with. Value function V mu is something that we are all familiar with. What Q function is saying, Q mu is saying, I'm looking at the reward, I'm using the transition kernel, but my future value is going to be V mu. Okay. Advantage function is a difference between the Q function and the value function. What happens at mu star at the optimal policy? What happens to the advantage function? So remember that we are maximizing here in this particular problem statement. So V mu is the maximum reward you could ever get. Q mu is the reward that you will get if you pick some other action. So what is some other action minus the maximum you can get at the optimal solution? So at the optimal solution, advantage function is going to be negative. Okay, that's so if you're estimating the advantage function, using simulations, and it turns out to be negative at all IU pair, I mean negative or 0 at all IU pair, it means you are sitting at the optimal policy. You don't have to do any further updates. So that's the advantage function. Policy advantage function is slightly complicated. So I use the current advantage function. I use the policy mu prime. Okay. So I'm looking at the current advantage function. I use the policy mu prime, and then I multiply it by, oh, this one is, okay, yeah, this one is a vector. So this is also a vector because you have a matrix getting multiplied by a vector. This vector, in this particular vector, it's a vector in I, and then mu prime is averaging all the u component of this advantage function. So this is also a vector. So this is an RS.
The left side is actually should have an I.
This is an I. Oh, yeah, that's right. No, this is not a function of I. So I'm multiplying matrix by something. Let me do it dot. That's right. Yeah. So I want to treat this as a vector. So I'm just going to keep it like this. So now it becomes a vector. Okay, maybe I'll do it like this. This is I, this is I, this is I. Now I've created a vector, and this is not a function of I, because this one would correspond to the row. This k component here would correspond to the kth row of this particular vector. So it's not quite a function of I. Okay. Compactly, I can write it in this particular format. Matrix multiplied by a vector, multiplied by a matrix, multiplied by a matrix, multiplied by a vector. So this is an RS. This is the difference of the two policies, mu prime and mu. And so this R is averaged with respect to this difference in policies. This P is averaged with respect to this difference in policies. Any questions on these notations?
Looks a little familiar, like the trust gradient forest optimization.
We'll talk about it. Yeah.
Oh, okay.
Yeah. So the initial, so I'm developing the general theory first, and then we'll specialize it for policy gradient, and then we'll specialize this for TRPO. Okay. If you already know all of this, why are you sitting in this class?
I know somehow.
Okay. All right. Yeah. So we are doing the derivation of TRPO algorithm. Towards the end of the class, we'll get there. Okay. All right. So no further questions. Okay. Now I'm interested in V mu prime minus V mu. It's given by sigma mu prime R mu prime minus sigma mu R mu. I'm going to add and subtract some terms, so I get something like this. I want to focus on this particular term. So what is sigma mu prime minus sigma mu? This is I minus alpha P mu prime inverse minus I minus alpha P mu inverse. I'm going to write it as I minus alpha P mu minus alpha P delta inverse minus I minus alpha P mu inverse. Okay, so it turns out that this P mu prime can be separated into P mu and P delta terms, because remember delta is mu prime minus mu. So I can do this separation, defining those matrices appropriately. Okay. Now here is a result from matrix A plus B inverse equals to A inverse minus A inverse B A inverse plus small o of B square terms. No, small o of B. Okay, so you will have higher order terms of B. Yeah, you will have higher order terms of B, but this is the first order term. In this particular case, A is an invertible matrix and B is a small matrix. B is a small perturbation to this invertible matrix. So the inverse can be written in this fashion. Any questions on this? This is an identity from any complicated books on linear algebra. But there aren't too many complicated books on linear algebra. Most of them are written for undergraduates, so they don't consider this. But if you look at a graduate book in linear algebra, somewhere this sort of identity would be discussed. Okay. I'm going to apply this particular condition here. So I have A plus B inverse. I can write it as A inverse minus A inverse B A inverse. Okay, so I have sigma mu prime minus sigma mu equals to sigma, or rather I'll write sigma mu prime equals to sigma mu plus alpha sigma mu P delta sigma mu plus small o of delta. So this is my A, this is my B. Remember, B has a negative sign. So this negative and the minus alpha P delta, both of them gets multiplied and we get a positive sign here. And the sigma mu is A inverse. So in particular, this statement, this is equal to alpha sigma mu P delta sigma mu. Okay. Oh, plus the small o term. Small o of delta. You can think of it as a Taylor series expansion also, first order Taylor series expansion, but somewhat in a matrix domain. So we are not doing first order Taylor series of vector, we are doing first order Taylor series of matrix inverse. Any questions so far? Okay. So let's look at this. So this sigma mu prime again can be written in this particular fashion. So I have this sigma mu prime, I'm going to write it in this fashion. I have this sigma mu prime minus sigma mu. I can, okay, so let's write it down. Okay, so I'm going to substitute this expression here, and then I'm going to substitute this expression here. Okay, and let's see what kind of magic we can create on the blackboard. I'll write it here that my L mu prime is sigma mu R delta plus alpha P delta sigma mu R mu. I will need this expression. Okay. So I have V mu prime minus V mu equals to alpha sigma mu P delta sigma mu R mu plus sigma mu R delta plus alpha anything that you noticed there in that expression? Are you noticing something there?
In the first expression, there are two sigma mu's.
That's right. That comes from here. Sigma mu P delta sigma mu. A inverse, B A inverse. Okay. So A inverse comes both sides. So that's this term there. Yes.
So the R delta, I guess did we define that?
So delta
Delta was mu half.
mu prime minus mu.
But does that mean that R delta is?
R delta is summation of reward I comma u mu prime u given I minus mu u given I, and this is delta u given I.
So explain it. So it's like you can take the difference of the mu's, and that also means you can take the difference of the r's.
Yes, that's right. So this is so delta is defined as mu prime minus mu. Mu prime. So mu prime and mu appears linearly in this particular expression, so it kind of follows from the linear algebra. Any other question? This is the most important step, okay? Same way P delta can also be defined. So in P delta also mu prime and mu would enter linearly. Subtract the two terms, you get something which is P delta. Yes. Two of the same what? Okay, so this one contains one delta, this one contains one delta, this one contains two delta. Okay, so this is part of my small o of delta terms because it contains two deltas. So all the higher order delta terms are separate. It's absorbed in this small o of term. What about this thing? Does it look familiar? What is this equal to? Sigma mu R delta minus, no, R delta plus alpha P delta sigma mu R mu. Is this something familiar? It's the same as policy advantage function. Okay, so this term is the same as policy advantage function. Where I have higher order terms. So I have policy. So this is L mu of mu prime plus small o of delta. Any questions so far? Okay, so this is the first order Taylor series term of the derivative, and these are the higher order terms for the derivative. If you expand this f of x plus d minus f of x, this is what it looks like. So higher order terms and the first order term. If you look at the first order term closely, it's actually a linear function in mu prime. So this one is a linear function in mu prime. So what you have is a linear function of mu prime. There are a lot of matrices here, so I'm not discounting that, but it's a linear function in mu prime. So you have a term that is linear in mu prime. Of course, when we do the gradient descent step, we are looking at the first order descent direction. We ignore the higher order terms. We just look at the first order term. And we find a mu prime that minimizes, in our case, I want to maximize the policy advantage function. So this is my original objective. This is my objective. I have to multiply it by rho transpose. So what I have to do is at every iteration k. So how do we start? We initialize the policy. So step 1, so of policy gradient. Algorithm. Step 1 is initialize mu 0, the initial policy, whatever that policy is. So remember when we were talking about the Uber example, what was the initial policy? Just pick the closest driver to the rider and match them. That's my initial mu naught. And then compute step 2, mu k bar equals to argmax mu prime L mu k mu prime, which is this policy advantage function. I'm not adding the higher order terms. Remember, we kind of ignore the higher order terms. So I maximize the policy advantage function with respect to mu prime. And then I set mu k plus 1 equals to 1 minus, alpha is already used. Step size. What is the step size? Gamma. Was gamma the step size used? Theta. Okay.
No, beta.
Beta. Okay. 1 minus beta k mu k plus beta k mu bar k, and then k plus 1. Okay, so far we are not in the simulation domain. We are still in the deterministic domain. So in deterministic domain, I know all of these things. I can do all this I can compute these matrices exactly. I can solve this problem exactly because it's a linear problem. And then I'm going to do the policy update in this particular fashion, and I'll keep doing it. What kind of guarantees do you get in gradient methods? If you have a highly non-convex function, this is a highly non-convex function in mu. What sort of guarantees do you get in non-convex function? It converges to a local maxima. Oh, I need to do row transpose. Sorry, please add this row transpose because that's what I'm trying to maximize. So I have to do a row transpose here. Okay, make that correction. So anyways, this particular policy gradient algorithm converges to a locally optimal solution. And generally speaking, over the last 20 years, people have found that the locally optimal solutions are good enough for applications. You don't have to have the best algorithm. You just have to have something that makes you $1 billion per year. That's good enough, right? So you can do policy gradient and you can get to a policy mu naught that makes you $20 billion a year, and then you are happy. That's what Uber is doing. That's what Google is doing. That's what everyone else is doing. And that's what LLM companies are doing. So this is the algorithm used for training LLM as well. Any questions so far? No questions? Awesome. What's better than the steepest descent? So that's the steepest descent algorithm. Okay, what is better than steepest descent? Newton's method. What do you do in Newton's method? Okay, that's a good point. So you can use momentum, you can come up with momentum version of this. I don't know if somebody has actually done it or not, but certainly momentum method is better than steepest descent, so you can get maybe some amount of speed up. But Newton's method is certainly much better than steepest descent. What do we do in Newton's method? How do we get the descent direction in Newton's method?
Inverse.
Yeah, how do you get that inverse thing? Yeah.
Is the Hessian?
Yeah, you look at the Hessian, right? So you look at the Hessian. What does that mean? Like, how do you get to that Hessian part?
It's an algorithm that computes A inverse B very quickly. I forgot the name.
Okay. Yeah, so you are right, but there is something precursor to that A inverse B part that you are getting to. What's the precursor? Anyone remembers? So remember, we ignored this second order term here, right? We said that I don't care about the second order term. I want to do the steepest descent, and I got to this algorithm. If I don't ignore the second order term, I get to the Newton's method. Okay. So now I want to go to O of delta square. So I want to look at what the second order term here looks like. Okay. In order to get to the second order term, I need to know what the second order term here looks like. Okay, so let's see what the second order term here, what does that look like? Okay, where should I write that? Okay, let me just let it be here. I'm going to write it here. A plus B inverse equals to A inverse minus A inverse B A inverse minus or plus A inverse B A plus B inverse B A inverse. So this is an exact expression, by the way, but I want to get the order of delta cube terms or delta square terms, so I'm going to write it as A inverse minus A inverse B A inverse plus A inverse B A inverse B A inverse plus small o of B square. So this is the exact term, and this is an approximation in the sense that you have small o of B square term towards the end. Okay, so I'm going to write down the expression, so you can do the same derivation that whatever we have done. You can essentially follow the same steps using this particular expression now. and you will get to the following conclusion. This is what should I do? I don't want to write the whole thing, so let me just write down the final expression for the second order term. It's L mu prime plus alpha sigma pi sigma mu p delta L mu prime. Yeah. Plus small o of delta square. If I expand this, what I have is alpha sigma mu p delta sigma mu r delta plus alpha p delta sigma mu r mu. This is what the second order term looks like. And what you tend to do, yeah, you have a question?
Yeah. You talk about the method being better than like this.
Yes.
We were talking about it. We're still not talking about global.
That's right. We are still, yeah.
Converting faster to this.
To whatever the local minimum you have in your arsenal. Yeah. So generally speaking, if your function looks something like this, and you start from here, you are going to converge here. If you start from here, you are going to converge here, right? So if you pick the initial condition mu naught here, you are doomed to reach this particular local minimum. You cannot go anywhere else. Okay, even though
So in deep learning, typically they set the step size much larger than that which would take you to the closest minimum.
Yes.
That's very important. So is that done here, or do you actually choose a small step size so that you actually do converge to the closest minimum?
I don't think people have spent much time in deep reinforcement learning, where you apply this. So you don't really focus too much on the step size. You just pick some small step size and you proceed. They don't talk about, can you pick a large step size and maybe you avoid local minimum or global minimum. So all of that stuff is not being studied in the reinforcement learning area. Okay, so they pick some small beta k and then they start running this algorithm, iteratively. And some people have studied classes of MDP where this would take you to global minimum. Okay, because of the way the function approximators are defined and because of the way the transition kernel is and so on. But we are considering more generic algorithms right now and not specific models. Okay. Now, here is the problem. When you are doing Newton's method, you ignore this term and you maximize over the first order term and the second order term with respect to mu prime. It turns out that the second order term, which has two deltas, so this is mu prime minus mu and this is mu prime minus mu, it's actually extremely hard to do this optimization in simulation. Remember, we are talking about right now we are talking about deterministic algorithm, we are not talking about stochastic algorithm. So in deterministic algorithm, you can still do this. If you knew all the models and everything, you can do this. But because in simulation-based algorithm, computing this is much more difficult. Computing this is very easy, the first order term, but computing the second order term is very difficult. So what happens if computing D is very difficult, then what do you do? So imagine you're solving a Newton's problem and you have a second order term, and it's difficult to compute the optimal solution D star, which is the descent direction, including the second order term. Then what's the typical approach? The typical approach is to approximate the second term. Okay, approximate it to something that's much easier to compute. Okay, so that was the insight. So this is the algorithm this is the policy gradient algorithm is for, it was used with appropriate modifications for various cases. It was used until 2014-15, and then in 2015 this paper TRPO came out. So let's talk about TRPO algorithm. Trust region policy optimization. (2015). Anyone knows who this guy is? No? No, he didn't develop PPO, he developed TRPO algorithm, which is what I'm going to talk about. So he's co-founder of a little known company called OpenAI. And while he was designing this TRPO algorithm, he was also thinking about joining OpenAI as a founder, as a co-founder. Okay, so this is the same time. 2015 was the time when I think he graduated in 2016 with his PhD, and then he joined OpenAI at that time. So he's a co-founder of OpenAI. Okay, so remember, he developed TRPO algorithm and he became a billionaire. I'm developing the infinite dimensional version of it. So I'm on track, on the same path to becoming a billionaire. Okay, anyways, so what's his idea? His idea is, this term is extremely difficult to compute. I don't want to compute this term. It's difficult. So let's try to come up with an approximation to this term. Yeah.
Is it difficult to compute for a given mu prime, or is it difficult to optimize over a mu prime?
It is, no, actually that's a great question. So for a given mu prime, you can actually compute it. You can actually also do the simulation and compute this expression. The problem is when you're doing argmax over mu prime, then you don't quite know what mu prime you're going to compute. So that becomes the bottleneck. Okay. So he is doing, so then let's go back to theory. The theory is minorization maximization algorithm. So I have a function, I want to maximize f of x. X is in Rn. The function looks something like this. This is my f of x. I'm sitting here at x. I want to get to the maximum, this point. Okay. The idea in minorization maximization algorithm is that I'm going to minorize the function at this particular point. What is minorizing the function mean? I'm going to construct another function that is below this function, the original function. So this is my g of let me call this xk, g of x xk. We have not used g so far, right? I think it's okay. Okay, so I'm going to construct this function g, which is strictly below f, and it meets the function exactly at xk, at which I'm trying to minorize the function. So the property that g must satisfy at every point is, let me call it gk, because at every point you will have a different minorization function. So gk of x xk is less than equal to f of x for all x in Rn, and gk of xk xk is equal to f of xk. And then I'm going to set xk plus 1 is equal to argmax x in Rn. This is known as a minorization function. Okay, so what happens in the minorization function? I construct a function that sits below f of x, but it meets f of xk at xk. So this is evaluated at xk, and this is f of xk. So I construct this minorization function, and then my iteration is xk plus 1 is the argmax of the minorization function at time k. Once I reach xk plus 1, I'll minorize the function again, and I'll keep running this iteration again and again. So once I construct, so this is my gk, this would be my xk plus 1, and then I'm going to minorize another function. I'm going to find another function gk plus 1 here, and I'm going to optimize. I'm going to get xk plus 2, and then I'm going to minorize again at this point. That would be my gk plus 2, and so on and so forth. And I'll eventually reach the maximum value, a local maximum value of that particular function. Any questions on this? Yes.
I think EM algorithm.
Yes, it is a instantiation of minorization maximization algorithm. Yeah.
Conceptually similar or the same.
Not yeah. So this is the theory, and that is an application.
Oh. Okay.
Yeah. Okay. So this is the there are some cool books written on minorization maximization stuff. algorithm. That's the name of the book, and it has a whole bunch of application, which EM being one of the application. I don't know much about EM, but I know that many people talk about EM, so that's how I know that this is an application of this algorithm. And people have used this class of algorithms in genetics. I don't know why, I don't know how, but that's where the genesis of this idea came from. Okay. All right. So I have this this term v mu prime minus v mu. So remember, what I have to do is I have to find v mu prime minus v mu greater than equal to something, and hopefully that something is a concave function, so that way it's easier to optimize a concave function. So I have the first term, which is linear, so it's easy to optimize. The second term is the one creating the problem, so I need to find a lower bound on this particular term. That was the idea that they had, and it turns out the 2015 paper, it said that this particular term, this whole term, is greater than equal to minus 4 alpha over 1 minus alpha square I have no idea what they are writing. Okay, minus 4 a mu infinity and dkl mu prime mu. No, mu prime. Yeah, this is correct. And the way they define, how did they define this? This is max over all I, KL divergence between mu and mu prime So each of the mu I is a probability distribution over U. So you take the KL divergence between the two, take the maximum over all I, and that's what this bound looks like. It's a fairly loose bound. This inequality. So this, by the way, the thing that I want to note here, this is a constant. This is a constant. Here is a negative sign. This KL divergence is convex in mu prime. So what ends up happening is you have V mu prime is greater than equal to V mu plus L mu prime minus some constant C times dkl mu prime. This one is not a function of mu, so you don't consider it. This is a function of mu prime. It's a first order term, and then this is a concave function. So with a negative sign, it's a concave function of mu prime, which is multiplied by a constant. Naturally, the constant depends on a of mu, but you can also get a lower bound on a of mu infinity, and you can replace it with a universal constant C. Okay, if your costs are bounded, alpha is given, then you can replace it with some universal constant. And this is the problem. This is the final result that you come up with. And now you have a linear function, a concave function in mu prime. You are good to go in terms of optimizing it, maximizing it. And that's your TRPO algorithm. Where should I write it? Policy gradient. Well, TRPO does a little bit more. So let me write it. TRPO. Step 1 is to initialize. Step 2 is everything else remains the same. Mu bar k is arg max of mu prime L mu prime such that dkl mu prime less than equal to epsilon, and then mu k plus 1 equals to 1 minus beta k mu k plus beta k mu bar k. That's your TRPO algorithm. So another thing that they did in the paper, they said that instead of trying to find what this constant C looks like, let's just add a constraint that the scale divergence is bounded by some hyperparameter epsilon. And we will keep optimizing this particular objective subject to this constraint. And the PPO algorithm, which is the next version of this algorithm, PPO came in 2016, right 1 year after the Schulman's paper. And PPO algorithm said, let's just keep updating this hyperparameter at every time step, because we don't know what this C should look like. We don't have the knowledge of all these numbers. So let's just keep updating this hyperparameter at every point of time. And that's the PPO algorithm. And this algorithm is amenable to doing the optimization through simulation. So instead of trying to compute this exactly, so remember right now all of these expression needs to be computed exactly, but you can actually use simulation-based methods to compute these two quantities, and then you can do the argmax. So we'll talk about that in the next class. We are sort of out of time. But here is the idea, basic idea of how do you do this. So these are deterministic methods. How do you convert a deterministic method into a simulation based method? Okay, so you've done I mean, this is part of your assignment right now, but so you will appreciate what I'm going to write on the board, assuming you have already started working on the assignment. Okay, so what's the problem statement? I have xt plus 1, which is distributed according to a Markov chain, and I want to compute the expected value of summation alpha raised to t f of xt. T goes from 0 to infinity. Okay, so what do they do? I want to compute this particular term, but remember I have to compute the expectation of this infinite sum. But I only have a simulation tool that's going to give me trajectories of xt. Okay, it's not going to give me xt exactly. So I can only generate trajectory. So I can get x1 to xt. I can generate maybe these trajectories, but I can't really compute the expectation. So what's part of your homework? Your homework part is to show that if you do summation of alpha raised to t f of xt, t goes from 0 to capital T. If you do this, you essentially end up converging. If you have multiple such sample paths and you add it up, in distribution, you kind of converge to the expectation. Okay, so that's something that's part of your homework. So you will see it in your, if you solve the last problem of your current homework. But essentially, wherever you have this expectations, okay, which is what we are going to talk about in the next class, wherever you have this expectation, you replace that expectation with the simulation, discounted simulations, and then you use that simulation in order to compute the value, and then after that you solve this argmax problem. Okay, so we'll talk about that in the next class, and we'll talk about TRPO algorithm, PPO algorithm, and then we will talk about general state space MDPs. Okay, and the way general state space MDP differs from the finite state space MDP that we have been talking about so far is you add a function approximation layer on top of all the existing simulation based methods that we have talked about. Okay, so once again I'll introduce some notation and it will make the entire derivation extremely easy. Okay, so this derivation that I'm doing here, if you go back to original papers, the derivations are extremely long. And the reason why those derivations are long is because I use this matrix identity, which is easy to understand matrix identity. Those derivations are trying to derive that matrix identity by differentiating each and every term, and it makes things very complicated. Okay, so we banged on the matrix identity in order to come up with the derivation that's much simpler and easier to understand and present in the class. Okay, so thank you everyone, and I'll see you guys on next Tuesday. Thank you.